Okay. Good morning, everybody. Today we're going to be continuing with our review of interatomic forces. But to do that, I thought we'd take a step back and review some of the principles of electrostatics. So really, the starting point for all of these interactions is to say we have a charge sitting out here some point in space, some charge Q. We want to know what happens if we introduce a test charge, capital Q, at some other point. Well, we can connect a vector and label it script R, and we can write down the experimentally determined and very familiar Coulomb force that exists between the charge and our test charge. So here we have just some constants. Then the product of the two charges divided by the magnitude of that radius squared multiplied by a unit vector in that direction. That's very good. As you may have noticed, this is a very special and curved R. But with this empirical definition of a force, we can factor out our test charge, Q, to see what would just be the effect in empty space if we only had the charge, little q, and the remaining quantity we call the electric field, capital E. So how could we define an electric field? Well, we would simply say the electric field is the same constants with a sum over all of those little source charges. Just take all those little charges, just add them on up, and divide them by the square of all the relevant vectors and all their little directions, also indexed with an I. Isn't that just a great formula? And the way we can understand this is in terms of the following picture. Imagine we have some coordinate axes like that. We want to say this is our origin. We want to place our point of observation, P, somewhere out there in space. And we're going to draw this nice vector, little r, out to that point. Then we have the point where our charge is. We're going to label that guy R prime, also a vector. And then to connect those 2 points, that's going to be that familiar script R. Not hat this time, full length. So with this in mind, what if instead of a collection of point charges, little q, we wanted to move to a continuous distribution of charge? How could we rewrite this formula, which is in terms of discrete charges, Qi? Well, the symbol we use for a continuous charge density, rho of R, which is equal to the charge at all positions divided by the volume that it occupies. Just do a very similar equation, but replace a sum over charge with a sum over volume. But since it is a continuous distribution, we use a fancy sum, a big curly S, just for that. So we'll say it's a function of the prime coordinates. There's our script r again, and multiplied by the volume d3r, also in the primed coordinates. The direction, of course, would still be in the direction of that script r if we wanted to include it. But there's a few really meaningful equations that we want to get to besides this definition of the electric field. Now, for those of you out there who aren't really a fan of these big curvy S's, these integral equations, we'll skip a couple steps here and write it down in differential form. Now, in differential form, we're going to use this lovely vectored triangle called the gradient operator and act that on the electric field instead. So we pay the price for getting rid of this integral by adding this derivative on the left-hand side. But now we just get out that rho that we had there before, that charge density. And only one of the constants survives, that epsilon 0, epsilon naught. So these are the two major definitions we're going to use for how a source, this charge density, leads to an electric field shown in either of those two equations. Isn't that just lovely? Now there's one more quantity I'd like to introduce to y'all, and that's the concept of the electric potential. Oh dear, I've run out of space. That says potent. Know that there's a shoal to follow. Now, one way to define this quantity V, which is the electric potential, is to say that it's an integral from the origin out to the point R that we're measuring it at of the electric field with respect to the path that we take to get to that point, dl prime. But really, a more useful way to phrase this would be, again, to remove this sum on this side and replace it with a derivative on the other side. So now we can say that E can be written simply as the gradient of some potential V, just like that. And you can't forget this minus sign. Oh, minus signs are so important. But remembering our previous differential form for E, we can also arrive at Poisson's law, which is if we just take two triangles, or the Laplacian of the potential, that we arrive at the charge density divided by epsilon 0. So this is how, starting from the source of our charge, this rho, we can arrive at the potential in terms of this Laplacian. And indeed, you can solve this particular form of the equation. And with this potential in mind, there's one final thing that we want to discuss. And that is simply, what is the work associated with these configurations? Now remember, work just has units of energy. So in one sense, we're asking, what is the energy that it takes to assemble these charge configurations? And very simply, if we want to assemble some total charge Q, we would just multiply that by the potential. Just remember, the potential had to do with an integral over the electric field from the point we're measuring to the origin. But equivalently, if we don't have just a single charge Q to speak of, we can of course integrate a density of charge over the volume. So we just simply take that rho, multiply by the potential, integrate over the volume, and really these are equivalent definitions, just depending if you want to talk about an individual charge Q or a density over a volume. And really, that's how I want to leave you with today. Just really a lot of equations that we've handed down that hopefully will help make us get a little farther in our next video.